I've been revisiting microcomputer architecture lately. Can we start by comparing von Neumann and Harvard architectures?
Absolutely. Von Neumann uses a single bus for both data and instructions, which can cause bottlenecks. Harvard separates them, enabling parallel fetches common in DSPs and microcontrollers. Which use case interests you more?
Embedded systems, actually. Harvard seems dominant there. But how do modern hybrids like modified Harvard architectures bridge the gap?
Great question. Hybrids use split caches, L1 for instruction/data, but a unified memory space. Take ARM Cortex-M. It's Harvard-like for speed but simplifies programming. Trade-offs?
Trade-offs indeed. Unified memory eases development but sacrifices throughput. Do you think RISC's flexibility could disrupt this space?
Potentially. RISC's modular ISA lets designers add Harvard-like features per application. For IoT edge devices, that's a game changer. But ARM's ecosystem is entrenched. What's your take?
Ecosystems are sticky, but RISC-V's open-source model could accelerate niche optimizations. Shifting gears, how critical is DMA in modern microcontrollers?
Crucial. Offloading data transfers, e.g. ADC to memory, saves CPU cycles. STM32's DMA even handles peripheral-to-peripheral transfers. Ever worked with circular DMA buffers?
Yes, for audio processing. But configuring burst modes was tricky. How does DMA prioritize requests when multiple peripherals compete?
Priority is typically hardware configurable. NXP's MCUs use weighted round-robin, while some TI parts allow dynamic reprioritization. Interrupt latency becomes a factor. Ever measured it?
Only empirically. Speaking of interrupts, how do RTOSs like FreeTOS handle nested ISRs differently from bare metal?
RTOSs add layers. Context saving, scheduler invocations post ISR. FreeTOS from ISR APIs manage this safely. But bare metal ISRs are leaner. Trade-off between complexity and control.
Makes sense. For hard real-time systems, would you ever recommend a superloop over an RTOS?
Only for trivial systems. Superloops struggle with multi-rate tasks. A properly tuned RTOS with priority inheritance avoids priority inversion. Zephyr's recent improvements are worth exploring.
Zephyr's device tree model is intriguing. How does it compare to Linux's for embedded use?
Linux's DT is heavyweight for microcontrollers. Zephyr's kconfig plus device tree strikes a balance. Static configuration reduces runtime overhead. Ever ported a driver across both?
Not yet, but I've seen Zephyr's GPIO API abstracts hardware quirks well. What's your view on memory-mapped versus port-mapped I/O for micros?
Memory-mapped dominates now. Unified addressing simplifies compilers. x86's legacy port I/O lingers for backward compatibility. ARM's MMIO even handles bit banding for atomic access.
Bit banding's a lifesaver for shared variables. But what about emerging non-volatile RAM like MRAM? Could it disrupt the memory hierarchy?
MRAM's persistence plus speed is promising, but cost/endurance lags. For now, it's niche. Think spacecraft logging. NVDIMMs might hit micros sooner. Ever benchmarked FRAM versus flash?
Yes, FRAM's write speed blows flash away, but density's an issue. Switching to interfaces, is SPI losing ground to I3C in sensor hubs?
I3C's multi-drop and in-band interrupts are compelling, but SPI's simplicity keeps it alive. MEMS sensors still default to SPI. Have you tried I3C's dynamic addressing?
Not yet. My current project uses QSPI for external NOR flash. Speaking of storage, how does eMMC compare to SD cards for industrial temps?
eMMC's soldered reliability trumps SD's connectors in vibration-prone environments, but SD's removable for field updates. SLC and remains king for longevity. Ever hit wear leveling bugs?
Once a bad FTL implementation bricked a logger. Let's talk security. How are micros handling Spectre meltdown mitigations?
Cortex-M33's Trust Zone helps, but timing attacks still haunt caches. Silicon vendors are adding speculative execution barriers. Rust's borrow checker could prevent some exploits. Are you adopting it?
Experimentally, the learning curve's steep. Back to hardware. Any thoughts on RISC-V's vector extensions for DSP workloads?
RVV's modularity is brilliant. It's like ARM Neon but scalable. For tiny ML, it could displace proprietary DSP cores. Seen any benchmarks versus Cadence Tensilica?
Not yet, but I'm eyeing a RISC-V plus RVVMCU for motor control. Which brings me to PWM peripherals. How crucial is dead time insertion in hardware?
Vital for H-bridges. Software timers can't match nanosecond precision of dedicated blocks. ST's HRTIM is overkill for most though. Ever used a CPLD for custom PWM?
Once synchronized 16 channels for LED matrices. But modern MCUs like the RP2040's PIO are stealing that niche. How programmable is too programmable?
PIO is a game changer. But debugging state machines gets hairy. XMOS's X-Core still wins for hard real-time multi-cores. Where do you draw the line between MCU and FPGA?
When latency demands sub-microsecond determinism, FPGAs rule. But Lattice's ICE 40 plus RISC-V soft cores blur the lines. Ever tried Chisel for hardware/software co-design?
Chisel's productivity boost is unreal. Generating Verilog from Scala saves months. But the toolchain's still maturing. Speaking of trends, how will chiplet-based micros evolve?
Chiplets could let us mix and match RISC-V cores with analog chiplets. But interposer costs must drop. TSMC's 3D fabric is promising. Will we see open-source chiplets?
Google's OpenMPW hints at it. But EDA tools remain a barrier. Meanwhile, analog's still a dark art. How's your team handling mixed signal validation?
Lots of Spice plus Python co-simulation. But back to digital. Any thoughts on memrestore-based micros for neuromorphic computing?
Still lab curiosities. Variability kills yield. But for edge AI, analog compute in-memory arrays, like Mythics, are closer to production. Ever benchmark them against quantized NN accelerators?
Not yet, but I'm skeptical about analog's precision. Shifting to power. How low can sub-threshold CMOS designs realistically go?
Ambique's Apollo 4 hits approximately 6 microamperes per megahertz. But leakage dominates below 28 nanometers. Energy harvesting's the next frontier. Ever used a PMIC like the BQ25504?
Yes, Zoller plus supercaps for a weather station. But MPPT algorithms need tuning. Final question. Will quantum coprocessors ever integrate with micros?
Decades away for anything practical. But cryo-CMOS interfaces are being researched. For now, I'm more excited about photonic interconnects in microservers. Thanks for the deep dive.